Here we are. It's the physics video lecture, Physics 203, video lecture 19. Today we're going to work on the canonical transformation, and we're spanning a big arc, or is it arch? Either, in order to make it all the way through the entire system of theoretical mechanics. So the canonical transformations are a big chapter in Goldstein. We're going to do a limited version of that because we're using them primarily to get the Hamilton-Jacobi theory dealt with. Good. So anyway, we'll kind of take it from the top again. The canonical transformation. And we'll list the ingredients that we need for this. The idea is that in Hamiltonian mechanics, our coordinates and momenta are all independent dynamical variables. So we have, for n degrees of freedom, we have 2n of those dynamical variables. And we're interested in coordinate transformations because that's the way we solve problems. We get a transformation that allows us to see that there's a cyclic coordinate, and then we can move on. So we have a transformation from old coordinates to new coordinates of the most general form, qi of q1 to qn and p1 to pn. Could also explicitly be a function of time. Are we dealing with those? Check here. Yeah, explicitly a function of time as well. And then new momenta are likewise functions of all the old coordinates and momenta, P and T. Good, so that's clearly a much broader class of transformations than if you were only transforming those. So what do we need in order for these coordinate transformations to be canonical? We have to have the canonical equations holding. So this transformation, canonical, legitimate, call it what you want, is going to require that the Hamilton's equations hold. So Hamilton's equations, and remember those are the canonical equations. Hamilton's equations must hold for the new set of coordinates. And that would be to say that we have to have qi dot is equal to dh dpi, but we're going to call that new Hamiltonian with the letter k instead of h. Okay, so it's going to have to be a new Hamiltonian, or the old one, dh dpi, and pi dot equals minus dk qi, I equals 1 to n. Where k is the new Hamiltonian, and we'll see in a moment what's required for that. But the idea is you retain the structure of Hamilton's equations that you had before, and that's what allowed us to do all these things, for example, with phase space. So everything that you've learned about Hamiltonian mechanics holds true for the new system, for the new set of variables, if Hamilton's equations hold. So now we have to find the conditions for that to be possible. And we had seen that we could derive Hamilton's equations from a variational principle. We had the derivation of Hamilton's equations from a variational principle. That's what I did last time. look at what that was. Principle. So remember, we transformed this into the variation, and here I'll remind you where that came from. So we had H was PIQI dot minus L. So we substituted L by using L is PIQI dot minus H, so sum of PIQI dot minus H dt equals 0, leaving off the details. Okay. So that's how we said we got Hamilton's equations from a variational principle. Now, we need variation of the new variables. So these are, I'm using uppercase for the transformed ones, lowercase for the untransformed ones. QI dot minus K of QE DE. Is equal to 0, right? If it's canonical, then this variational, these are just equivalent, okay? New letters, new variables. So we're going to have that. And the condition for both of these equations, or both of these principles here to be true, which I'll write down here. So the condition for both this variational principle and this one to be true is that they differ, these integrals, these action integrals, differ by a complete time derivative. Condition for 1 and 2 is that I'll just write they differ by a complete time derivative. Let me go ahead and remind us of what that means. Complete time derivative. This is back when we were doing Lagrangian mechanics, which is where we had this principle in the first place. That was, here I'll use this piece of the board. So recall, S prime we're talking about the integrand right now, okay? So L tilde equals L plus D dt f of the coordinates and the time. So we had the equivalence of two Lagrangians if they differed only by, or if they differed by the complete time derivative of the coordinates and the time. Now, because we have these vastly extended coordinates, so to speak, we're going to get a much more extended version of that up there. Let me go ahead and write this down. Yeah, I wasn't actually talking about the action. The action is the whole integral. I was talking about the integrand, which was the Lagrangian. So we'll just formulate this and then have a look. So here, we're going to have sum of P I Q I dot minus H Q P and T is going to equal sum of capital Q I dot minus K capital Q capital P and T complete time derivative of a function. Now this function here can be a function of any of these, or actually any combination of the q's, the p's, and the t's, okay? Any combination of q, p, okay? Because they're all coordinates, okay? They're all independent coordinates. So we have to take this with a couple of examples. Yeah, so this is the criterion actually. So these are equivalent if they differ by a complete time derivative. So let's write this out explicitly. And actually I'll also note already that f is referred to as a generating function. Generating function of the transformation. So, as an example, let the generating function be a function of the old coordinates and the new coordinates, and I'm going to, this is just the terminology that Goldstein uses. It's just a certain type of generating function because there are many. So this is q1 to qn, p1, oh, sorry. Old coordinates, new coordinates, and time. Okay. And we're going to do a few of these because there's different types of these generating functions, but this is one type of generating function. Remember, all the q's and p's are just independent coordinates. Good. So now we go ahead and expand that out. So here we just copy what we have, pi qi dot minus h of old coordinates momentum time equals sum over new momenta, new coordinates minus k q, p, and t, like that. And now as far as this complete time derivative goes, we have to expand it out. So since it's like this, we do the chain rule, complete time derivative plus sum over df1 dqi qi dot, and under the same sum, or I'll write the sum again, df1 d capital qi dot plus, now outside, df1 dt. Okay. So now we're going to require, we're going to match coefficients, and that's the requirement that'll give us this equality here. So how are we going to match coefficients? We have df dqi is going to, so the coefficient of qi dot over here is p sub I. So we have old momentum is equal to df1 dqi, like that. So that's the one. Then we have, for the qi dot here, this one, those have to equal and cancel to get equality. So we'll have pi uppercase is minus df1 dqi. And let's go ahead and strike these while we're at it. So we have this, and now these are gone. And so what's left is that df1 dt is going to be equal to df1 dt is equal to minus k. So I'll even write it in a suggested form. Plus k no, let's not do that. df1 dt is equal to negative h plus k. Or I can write k minus h. Actually, this one's going to play a big role, so all three of them are pretty important. Let's put a box around each one. Okay, so let's set this up here and discuss these briefly. For our canonical transformation, so there's our generating function f. This is of the type type 1 of Q and Q. We'll do another one in a minute. But visible, yeah. We can see that if the generating function is not explicitly a function of time, the new Hamiltonian and the old Hamiltonian are the same, right? Because we got a 0, k equals h. And then this is a relation that shows how the new and old momenta are related to these these derivatives of the generating function. This is going to play an important role. Actually, all do. So that was the type 1. That begs the question: is there another type of generating function? And there's one more that we want to do. And this one I'll give you as a homework assignment. If you look in Goldstein, there are 4 types and then subtypes, but we just need these 2. So generating function, so for the generating function f sub 2, f sub 2 of q capital P and T. So we're looking at here function of the old coordinates and the new momenta, right? The original coordinates and the transformed momenta. Here it was the original coordinates and the new coordinates. So this is a different one. We find, and here I'm just going to write them down for us, and you guys will get these on the homework. Yes, here we go. So what do we get? We get E sub I, so old is equal to D F2 dq sub I, and q sub I d F2 d P sub I. Make sure I got those right. Yes. And the third relation is the same as before. df2 dt is equal to k minus h. call this a homework problem. This is a good one to go through with. And you have to do a Legendre transformation on this actually in order to make it work. So, show this set of relations by taking F2 equals F2 of old and T, and then you subtract off sum of Q sub I, P sub I. So make sure you see that these are the uppercase. This is uppercase, that's lowercase, those are the old ones. So what you do is you take this thing into the same calculation I did up there, and then you do df2 dt, expanding it out, and having subtracted this, just the way we did before in our Legendre transformations, off of the f2, that's how you're going to switch out those coordinates there. Okay, so both of these are important. I'm going to do an example using this formalism here, and when it gets to Hamilton-Jacobi, this one's actually going to be more important for us, okay, but they're both used similarly. So yeah, for the homework is to take this expression up into this calculation here, top of the board, and then again match coefficients, and you should then end up with these relations. Okay, good. Let's see how we're doing time-wise. Perfect. So I'm going to do an example. And now that I think about it, I'm going to use these relations. So I'll leave this board up there and erase this one. Let's see if we can fit it all on one board. Okay, this example is how to use the canonical transformation to actually solve a problem. So solving the harmonic oscillator. And what's our goal? Our goal is to find an even better set of coordinates. Now, harmonic oscillator is 1 degree of freedom, so what we're going to have to do is find a coordinate for the harmonic oscillator problem that is ignorable. Okay, we want to find a cyclic coordinate for the harmonic oscillator problem. So let's even write that by finding coordinates in which one coordinate, or in which that coordinate is cyclic. So finding coordinates slash, since there's only one coordinate, cyclic coordinate. Okay. That's our task. Harmonic oscillator with a cyclic coordinate. And what we're going to do is start with the Hamiltonian of Q and P. There isn't going to be any time dependence in the harmonic oscillator. So of course we know that's just P squared over 2m plus 1/2 K Q squared. That's our harmonic oscillators. Now what we can do is write 1 over 2m, factor out 2m, and then we would have p squared plus actually k over m. Is omega squared. That's it. M squared omega squared q squared. So this form is supposed to make something explicit, namely that we're looking at an ellipse. Okay, we get p squared plus m squared q squared, omega squared q squared. And yeah, that m omega squared, of course, is the k, right? If you divide that one there, so that's where that comes from. And I'll go ahead and write that. Omega squared equals k over m. So far, we're on familiar territory. And now we're looking for a transformation. And because we're looking at a sum of squares, so sum of squares is going to imply that we could try this. P is equal to a function of P cosine of Q, and Q is equal to a function of P sine of Q over m omega, right? So P squared plus m squared omega squared q squared, that would just give us this f of p cosine squared plus sine squared is equal to 1. So this is the ansatz for our transformation. So the next thing, k is equal to h because we don't have explicit time dependence. So then we have the 1 over 2m and then the f of p quantity squared. Okay. And if we could do that, you'll notice that's the new Hamiltonian. We would have cyclic coordinate, because there's no q in there. But of course, we don't yet know what the function f of p is. So what is f of p? Question mark. So for that, we'll start to use these relations right here. So f of p can be, first of all, eliminated from here. So I'm going to number these 1 and 2. So p divided by q, that gets rid of the f of p, and then we just have the uppercase q. So that would be m omega cotangent, m omega q cotangent q, where p is equal to m omega. Q is only here once. P over q, m omega cotangent q. So m omega q cotangent of q. And it's not all going to fit on one board, but here we have P is equal to df dq is equal to df dq. So there Q was not written in here. Q df dq. Now moving up to that space, so we have df dq from this relation. m omega q cotangent of uppercase q. So that's partial with respect to q. So we have f, which is the function that we're looking for, is equal to m omega q squared over 2 cotangent of q, capital Q. And that is our f of lowercase and uppercase q. As you can see here, we're using the function f sub 1. So now we have another relation that p is minus df d uppercase q. So now we'll get p is minus the derivative of this with respect to uppercase q. Not all going to fit on one board, but that's okay. Now use capital P equals m omega q squared over 2, and then the derivative of cotangent is 1 over sine squared of q. And now we're going to solve for q, lowercase, capital P m omega sine of q. Okay, just so we have that in front of us. Multiply 2 over m omega. And that was q squared. Do I have a square root there? Yeah. And before that, we had f of p over m omega sine of q. So now we're going to compare these two, and we can get the f of p out of this explicit expression for p. So comparing these two, we get f p, which was that unknown function, root 2m omega capital P. And now we're ready to get the new Hamiltonian, which is up here. And I'll write that right here. So now the new Hamiltonian is equal to 1 over 2m f of p squared 2m omega p. K is canceled, is simply equal to omega times p. So this is what our canonical transformation did. It turned this Hamiltonian into this new Hamiltonian, which is really simple. So let's see if we can go ahead and solve this. This shouldn't be bad. I think we have everything up there that we need. Okay. I'd like to have everything up there whatsoever, but I think we'll do this. So there's the new Hamiltonian. This we no longer need. Nice to have the old system up there as well. Okay. This should suffice. Because we even have the definition here, okay, of the omega. And we have the new Hamiltonian. So we'll put it all together here. We have, so now we have K is equal to omega P, that's the Hamiltonian, and then we have the canonical equations with Q dot is equal to dk dp, and P dot is equal to minus k d capital Q. Well, of course, we have a cyclic coordinate here. There's no explicit capital Q, so we immediately have P is constant. Okay. What about with Q dot here? Q dot is equal to dk dp, so Q dot is equal to omega. Yes, of course, equals energy Hamiltonian over omega, so we'll just write here E over omega. But if Q dot is equal to omega, and Q is equal to omega T plus, I'll just say beta, and if we go back into our definition of Q in terms of lowercase q, we're just going to get our sinusoidal motion again. So continuing, we're actually got room right here. Omega t plus beta, therefore Q is equal to root 2e over m omega squared, and outside of the square root sign omega t plus beta. So, and that's the standard solution to the harmonic oscillator. So this time we can kind of have it all up on the board at once. So to go through this again, we start with the Hamiltonian, and we're looking for a coordinate transformation that'll turn Q into a cyclic variable, and this difference of squares structure kind of gives the idea for that. Okay? Otherwise, you'd say, how did we pull that out of a hat? Really, because we know cosine squared plus sine squared equals 1, and we're looking at an ellipse right here. Okay, so that's how we came up with that idea, and then we figure out what f of p is using the differential equations, and then we find that new Hamiltonian. So this was that coordinate transformation. This is how we found a cyclic coordinate, okay, namely this form here. Then working with the Hamilton's equations, of course they're trivial, okay, and so you get this, right, you have a q dot equals omega, which is a constant, just omega t plus beta. And then when you go back into your definition, right, we know what f of p is, sine of q, and then q is the omega t plus beta. Good, so that's how that's done. Just to show that one can use it directly to solve problems. Our major application, though, is going to be different. Okay? So you can actually see quite a bit of this in the relevant chapter of Goldstein, but we're moving into the Hamilton-Jacobi theory. So we needed this very important intermediate step. And I think what I'll do is I'll just reiterate what we want on the homework. And actually, before I say that, we're going to find a general technique to turn all of the coordinates cyclic. We could say that's what's going on in the next chapter. So here we did a single coordinate. We found a way to find a new Hamiltonian in which that coordinate was cyclic. And our next technique is going to extend that to general systems, not just single degree of freedom. And if all coordinates are cyclic, then all of these new coordinates end up with this trivial form. Of course, all the work is as what we just did before. All the work goes into finding that new set of coordinates, but there's a systematic way of doing it. So what we need is the generating function. So what I had here was an F1 of Q, and T, and then we got those relations there. And this is the homework, is to go back to the derivation of this one and study that, and then find the relations that hold for F2 old coordinates, new momenta, and T. And we're not just going to solve we're not just going to solve the harmonic oscillator with this type, but we're going to solve a whole class of problems using this type. Okay. So you guys give that a try. It's easy, okay? So you guys do that, and we'll have those relations here. So what we had was, what we were going to find was that df2 dt is, as before, k minus h, and then df2 dq is going to be old. So these are the old, and df2 the capital P sub I is going to be Q sub I, like that. Good, so that's our task, and then I'm going to start off next time assuming this, using this, and moving forward. Good. See you guys next time.